In today's video, we're going to look at some characteristics of polynomial graphs. Now, when we're looking at these, there are going to be several problems, several functions that we'll look at that are not going to have nice integer coordinates. That being said, we will never expect you to find these points without using a Desmos graphing calculator. You can absolutely do these on a TI calculator. However, I know not everybody has access to one. So I am focusing on using the Desmos calculator with this. And to that end, all of your practices that need this in there to help you out with that, as well as your unit test, we will have that Desmos calculator embedded in there so you can do these in the same method. So let's look at some of these graphs. We're going to be pulling in some of the characteristics that we've talked about over our first lesson from this unit, as well as previously with our different parent functions. So our first function that we're looking at is example 1, f of x equals 1/5 x minus 3 and x plus 2 squared. Now, if you don't already have your video on a regular computer screen, laptop, or otherwise, I would definitely, pause the video, open it on a larger device. Please do not try to read this on or watch this on your phone. It's going to be real hard to see your text on here. Okay, so going over to graph this out. And you're going to see why in a second, why I've got this 1/5 out in front of my fraction. Now, I know you're going to see in a future video that, keeping fractions in here is not the nicest thing to do. But here's the reason I'm putting a fraction in that a value. Look at what happens when I take out that 1/5. So we actually have a very tall function that you need to scroll a bit to see it. And so that's why I have these fractions in here. It makes this graph a lot easier to see on a standard window size. So that's why we'll have those in there. And so the nice thing about Desmos, again, it's giving us all of our key points. So any of these intersection points, like our X-intercepts or our Y-intercepts, I'm going to go ahead and click on those just so I have those available. So now let's go ahead and sketch this out. So just like our previous video, we've got, let's see, we have it hitting at the -2. And it's bouncing at that point, so that's our double root that we see. We have a 0 at 3, and it goes straight through because that's a single factor. We have our y-intercept at -2.4, so about halfway through. And, whoops. And I don't know why that deleted on me. -3.7, so almost 4. And then another one at 3, and then we draw a graph. Excuse me. So I'm on my drawing tablet, so it's not coming out perfect. And we go up through. All righty. Okay, so let's list out our different properties. So our degree, well, we know we have a single root and a double root, so we have a third degree equation. That's our highest exponent. Our multiplicity is all added up together. And because that's an odd number, that is indeed an odd function. Our domain, well, if our pieces keep going to the left and keep going to the right, for our x's, we don't have any hiccups. So our domain for this, going back to the same notation we used before, x is such that x is in the set of all real numbers. Our range, same thing, keeps going top to bottom, no hiccups. So our range, f of x, is such that f of x is all real numbers. And in fact, anytime you have an odd function, you are going to have all real values for both your domain and your range. Our x-intercepts, again, very clearly marked on the graph. We have one at -2, 0, and another one at 3, 0. Our y-intercept, again, not as important for, overall behavior of the graph, but it lets us sketch this out really well. We have that sitting at 0 and -2.4. This is our new piece. So we're going to start talking about something called our absolute extrema. Now, we talked a little bit about minimums and maximums before with quadratics, but now with our polynomial graph, since we have so many different kind of humps and different areas in here, sorry, I'm just hitting the save every so often so I don't lose anything. we now have to think about these in terms of, is this absolutely the maximum for the whole graph, or is this just for this one section? So let's first write all of our minimums or maximums out. So this first kind of bounce here, hitting at -2. When we talk about our minimums and our maximums, we're going to talk about them in terms of our y values. So at this point, we actually have a relative max, because relative to that area, it is a maximum part of the graph. So we have a maximum of 0 at x equals -2. However, that is not an absolute max. It is only a relative max. We have this point here down at the bottom of this kind of trough. Again, we would call this a relative minimum, or min to abbreviate. We always look at this in terms of the y values, because again, how far up versus how far down have we gone? So we have a maximum, excuse me, I put these in the wrong spots. So let me just do this. We'll just erase. Come on, eraser. And I'll just rewrite that piece. Okay, so that was a relative max. We're going to put it in the second line for maximum. So our y value was 0 at x equals -2. Our relative minimum, bottom of the second trough, our x value is approximately -0.37. Excuse me, our y value is -3.7. Our x value is approximately 1.3, technically 1.3 repeating, it looks like. Neither of these are an absolute maximum, because we have other points that go higher on the graph or lower on the graph. So we call these relative. So in our future examples, if this is an absolute maximum, we're just going to show this by circling it. Unfortunately, there are no absolute maximums on this one, because our graph keeps going up to positive infinity and down to negative infinity. So we still have larger values that occur on that graph. Okay, this is where our increasing and decreasing gets a little bit more complicated. It's the same idea as what we did before. So we still have to say our different possibilities. And actually, let me change my color on here. So we have increasing. We always want to think in terms of, if I'm walking along the graph and I start on the leftmost piece, well, I start walking up. So I'm on an increasing piece. Then as soon as I hit this point, I'm going to be decreasing as I walk downhill, and then I turn around again here. So a lot of times we might call these relative minimums and relative maximums, we might call them turning points, because it's where we're going to be turning from increasing versus decreasing. For our increasing and decreasing too, don't forget we always use x values. So that's different from our maximums where we're using y's, or minimums where we're using y's. Increasing or decreasing, we're always using our x values to describe. So our first interval of increasing, we start all the way on the left of the graph, which means we start at -infinity. And then we stop at our relative maximum. Well, we know that point is at -2 for our x coordinate, so we stop at -2. And the way that we say we're going to have multiple intervals is we use this symbol, which is called the union. And that just means I've got multiple intervals. My next interval starts at the relative minimum, which according to our graph over on the right, was at approximately 1.3 repeating on our x. And it kept going up and up and up and up. So it goes all the way up to positive infinity. Our decreasing interval was between our relative maximum and relative minimum. So that's just between -2 and 1.3. All right, our end behavior. Again, this isn't new, so I'm going to go back to red. The pop's a little bit better on the screen, I think. So end behavior, again, as x approaches positive infinity, that means we're in this area. So as we're going to the positive x values, our graph keeps going up and up and up. So our f of x also approaches infinity. As we're approaching negative infinity, well, we're down here. And so as we move to the left, f we walked to the left, excuse me, that should be a negative. Please add that in. That then means our y values are going down to the negative infinity, so that is also negative infinity. Oops, sorry. I don't know why that is deleting on me. Let me go back over here. So x approaches positive infinity and negative infinity. And again, x approaches negative infinity, x approaches positive infinity. Alrighty, so let's look at our second graph. So again, first, I do not know why it's working. I usually use this on my laptop. I'm doing this on the larger screen so you can see both the notes and the graph at the same time. Okay, example 2. So before we graph this out though, let's think about this. Our degree on here, we know is going to be the highest exponent 2, highest exponent 3, add those together, we're going to have degree of 5. So that means we're going to have an odd function. So before I graph this out, I know what the picture is supposed to be. It's going to be similar to what we have now. We'll have our ends going in opposite directions, but we can also kind of predict a little bit with what we talked about last time with that negative sign out in front. That means they're probably going to be going in different directions. Let's go ahead and type that in and see what happens. So here we go. So f of x is equal to negative 1/5. Again, fraction just so we can see the whole graph easily. Oops. I'm using the arrow key to move over, and that's what happens if you're having that problem come up when you try to type things in. Just use your arrow keys, or again, on your keyboard, you can just hit the left or right arrow. So x plus 1, which has an exponent of 2, and then x minus 2, which has an exponent or multiplicity of 3. Ooh, that is a messy graph. Let's go ahead and zoom in a little bit. You can use your plus or minus keys, or I'm just using the scroll wheel on my mouse. And then just like we did before, let's go ahead and click on all of our turning points or intercepts that we see. And just like last class, we have one of these, which is a bounce. That's our double root or multiplicity of 2. And we have a wiggle through the 2. That's our multiplicity of 3. Alrighty. So let's sketch this out. So we have a negative 1. We have our y-intercept at, let's see, about 1.6, but then really, really close to that, we have, goodness. So negative 1, 1.6, and then just barely above it. And I know, let me pause for a moment. And let's see, so now we come down to hit our 1, negative 1, we bounce, go through our y-intercept and our top point, and then we kind of wiggle through the 2. Alrighty, so, and again, I don't expect your graphs to be perfect. It's all about trying to get our kind of overall idea of what's happening. Okay, domain, again, ends keep going in both directions are opposite directions. So our domain and range, same thing as the previous, all reals. So x is such that x belongs to all real numbers, and f of x such that f of x belongs to all real numbers. Okay, x-intercepts are just the roots that we have for our equation. So we have one at negative 1, 0, and our other at 2, 0. Y-intercept, that's our 0, 1.6. Again, not at a pretty spot, but again, this is why we're using Desmos. It gives us exact info. So now minimums and maximums. So what are the points where it looks like we come to the base of at least that section of the graph? Well, the only thing I'm seeing is this point over here, negative 1, 0. So our minimum, again, always referencing the y value first of 0 at x equals negative 1. But there are no other places where we come to a minimum. The rest of the graph, like once we get over that hump, we keep going down towards negative infinity. So unfortunately, that means there's no absolute minimum on this one. Same thing with maximum. We come to kind of the top of this section, but it's not the overall top of the graph. So that point was at, that's our 0.2 and 1.68. So our y value 1.68 at our x value equal to 0.2. There were no absolute minimums or maximums on this. Now, when we've had this happen with both of our odd functions. So that means when we start looking at an even function, we'll probably have an absolute minimum or maximum to deal with. Okay, our intervals. Again, if it helps, think of you're walking along the line. You start on the leftmost part. You're going to turn around at this point, which is at a -1, and you're going to turn around at this point, which was a +2. So are you starting as increasing or decreasing? Yeah, you're going to start walking downhill. So our first interval starts at -∞ up to our turning point at -1. Our next piece, we're going to keep increasing until we get to that topmost point, which was our x value was 0.2. So that's where we're going to turn around. So we increase from -1 up to 0.2. The next section is another decrease, and we keep decreasing after that. Are we actually turning around at that 2? So he's not actually a turning point because, yeah, we have a wiggle, but we're going to keep walking downhill as we go through that point. So we're going union, and we start at the 0.2, and we keep going to infinity again, referencing the x value. We keep walking to the right. That means x value there. So we didn't have a second interval, so I don't need that union symbol. End behavior. Again, as I move to the left, I'm up here. So this is to -∞. This is x moving to +∞. So as x goes to +∞, we're going to the right of the graph. We're going in this direction. So that means our f of x, our y values are approaching -∞. As x approaches -∞, and again, I'll fix that on the copy that I post, f of x in this direction keeps increasing, so we're going to +∞. All righty, so we have another one to check out. So example 3, look at your degree. So we have a cubic multiplicity of 3 and a single factor multiplicity of 1. So that means what's our degree going to be? 4th degree. So this is an even function. So we are going to have an absolute minimum or maximum somewhere on this graph. So let's go ahead and graph it. And again, at this spot, if you want to try this one on your own, go ahead, pause the video, graph it out, and then see what values you get compared to what I do in a moment. Okay, let's type this one in. So f of x is equal to 1/2, and I could have typed 0.5 if I wanted to, x cubed, and then times x plus 4. So again, I'm going to zoom out a little bit. Even with the 1/2, you'll notice our graph does go kind of far down. So I'm going to be kind of sketching it out. It's not going to quite fit on my graph, but that's okay. The big thing is I want to know where it's hitting the x and y axis, and it really only hits at 2 points on this one. We don't have anything else happening with the bottom piece of this graph, but I do need to know that bottom point. So here are our 3 important points. Okay, so we're hitting at -4 and 0. We have a bottom point at -3, 13.5. So I know I can't fit it on here, but I'm going to just label it. So that's at a -3 and then -13.5. I go through the -4, turn around at that bottom point, and then I wiggle through 0, 0, and keep going up. Okay, domain. Do the ends keep going on my graph? So that means our domain is still all reals. X belongs to all reals. The change is in our range. So if you look at the bottom of our graph, we have a bottom point. The end, nothing on our ends goes any further than that. So that means our function has to be bigger than all those values. Again, range is always y, so f of x is greater than or equal to negative 13.5. Okay, x-intercepts are just at our zeros, negative 4, 0, and 0, 0. Y-intercept happens to be the same point, 0, 0. You can have a point as both an x-intercept and a y-intercept. Well, now minimums and maximums. We definitely have a minimum happening at negative 13.5, and that's happening at x equals negative 3. And that is the absolute bottom piece of this graph. So that means this is an absolute minimum. So go ahead and circle him to show, yes, absolute minimum. Do we have a maximum? Well, the ends of our graphs keep going up. We don't have any other sections that have like a little, dip after we get to a point. Everything keeps increasing from that base point. So unfortunately, we just don't have any maximum. We don't count infinity as a maximum or minimum. It's just a concept of really, really big, but we don't actually hit an exact value. So we can't count it as a minimum or maximum. Okay, so again, visualize yourself walking along the graph. We have to start walking downhill. We turn around down here. We do not turn around at the squiggle. And so increasing interval, well, we don't start increasing until we get to this bottom point. So we start at negative 3 and we keep going to infinity. Decreasing, we started at the beginning, so negative infinity, and we stopped decreasing at negative 3. And again, don't forget, we use parentheses on these because once you hit that exact point, you're neither increasing or decreasing. If you were to pause at that point, you wouldn't be walking uphill or downhill, you're just there. Okay, end behavior. Again, as x approaches negative infinity, we're going to the left. As x approaches positive infinity, we're going to the right. So both of our ends go to the positive. So both of these are to positive infinity. Okay, quick review. We are dealing with functions and we are dealing with our x values and y values and such. So let's just do a quick review. This is probably back from Algebra 1, where if we're given a function, we're asked to find what is the value of f of x. And keep in mind, all we need to do for this is we're just plugging in our x values. So number 4, f of x equals 3x cubed plus 7x squared minus 6x plus 2. And we're looking for when x equals 3. So all I need to do is plug in a 3 anywhere I see an x. So 3 cubed plus 7 times 3 squared minus 6 times 3 plus 2. And yes, you could do this in a calculator, but just be very careful if you're going to do that, because if you misplace one set of parentheses, it will throw off your whole problem. Okay, so I will go ahead and raise things to the exponents. And again, I'm just raising the 3's to an exponent. That's one of the errors that I've seen on calculators before. If you forget those parentheses, depending on the calculator, it might throw off your results. Okay, then we need to do 3 times 27. I believe that gets us to an 81. Cool. 7 times 9, 63. 6 times 3, 18, and then plus 2. And then we're just adding, we're subtracting left to right. So 81 plus 63 minus 18 plus 2 is 128. So f of 3 equals 128. Okay, go ahead and pause the video, try 5, 6, 7. Again, these should be reviewed for you. But just in case, in a moment, I'll go through them. All right, number 5, f of 2 equals negative 4, 2 raised to the 4th, minus 2 times 2 cubed, plus 8 times 2 minus 11. 2 to the 4th is 16, minus 2 times 8, plus 8 times 2. And again, notice I'm kind of dividing up where I'm simplifying things out. So I have less of an opportunity to miss a negative in here. If you're doing this on the calculator, again, just be very, very careful that you're always putting in your parentheses and your exponents in the right spots. Wait a second, I have a negative 16 plus 16. That makes my life easier. So I need to do negative 64 minus 11. So that's going to give me a negative 75. So f of 2 is negative 75. Now, just out of curiosity, I could go through and check these on the graph too. So I'm actually going to do that with number 6. I'm waiting to do it until then because 75 I know is going to be hard to see on the graph. So f of negative 2 for number 6, negative 2 plus 3, and 2 times negative 2 minus 7, otherwise known as negative 2 plus 3 and negative 4 minus 7. And again, you probably could skip steps on this, but again, I'm just being extra careful. Negative 4 minus 7 is negative 11, because you know what happens when I go too fast. I don't want to miss any negative signs. And that's the biggest thing I do when I'm rushing. So I got out f of x equals negative, or it equals positive 11. So let's check this to see what it looks like on the graph. So I'm going to recenter. If I'm getting 11, that means I'm probably going to have an 11 show up on here. So let's look at this. So my original function f of x equals x plus 3 and 2x minus 7. So how in the world can I get an 11 out of there? Well, let's look at, let's see, x equals negative 2. This is why it's good to do things in multiple methods. Can you find my typo? Look at my first set of parentheses. So if I have negative 2 plus 3, what should that really come out as? Yep, that should be a positive 1 in there. So this is a 1, and 1 times negative 11 is a negative. So here's how I caught it. If we're looking at f of negative 2, that means our x value is negative 2. So negative 2 on the graph is right here. So I want to look along my parabola and see, well, where am I crossing this kind of vertical line of negative 2? And if I look right here, and it's rounding it off really, really specifically. There we go. Negative 2, negative 11. And I can pick that point right off the graph if I need to. And that's how I used it to check my work, to say, oh, wait a second, don't go back and double check my negatives, because I saw that my point was coming in below the graph instead of at a positive 11 above the graph. Okay, last one. Let's try number 7. So again, f of negative 1, 6, negative 1 raised to the 5th. Wait a second, what happens when you raise 1 to a number? And so this is really about being careful of your negative numbers. So here we go. Negative 1 squared, or negative 1 times negative 1, gives me a positive 1. So what's going to happen when I raise negative 1 to an odd power? It's going to give me a positive number. So this is a positive 1. Excuse me, negative for the odd function. And then negative raised to an even. Well, that's a positive 1. We have another negative 1 raised to an even number, so positive 1. So really the only one that flips around is this first one at negative 6. Then we have positive 3, positive 8, and then the 5 didn't have an x on it. Excuse me. So then we add these values together. So again, negative 6 plus 3 plus 8 minus 5, and we get out, well, that's anticlimactic. We get out a 0. Let's check it on the graph, just in case. Okay, f of x equals 6x to the 5 plus 3x to the 4 minus 8x squared minus 5. So at x equals negative 1, again, let's see here. There's my negative 1. Way down, where's my typo? Did I type it in okay up here? 5th minus x squared minus 5. Did you find it? I left off a negative. There we go, negative 8, negative 8, negative 8. So recalculate it. So we have a -6 plus 3 minus 8 minus 5 actually gives us a -16. So that means I've got to scroll all the way down, and there's my -16 right there. Awesome. Using this tool to check your work is a wonderful thing. As always, if you have any questions, concerns, comments, please, please, please let me know. And if not, keep going on your practice. See you later.